constant class members. So if you'd like to keep a data variable of the class constant, it's a good idea. So here, for instance, we could use some kind of integer stack, like container of integers, and we could define an integer stack size and keep it constant. Okay, so something very simple idea like this. So if this was not static, we would have to use initializer list to initialize it with this value. But if we make it static, which is really no reason not to make it static, because stack size becomes shared by all class instances, all object of this type, if something is made static, and constant is a very nice thing to share between multiple objects of this type. So static is kind of natural. And in case of it's static, and this data type is integral data type, such as character, integer, boolean, all types of integers, then it's okay to use this initializer, and this is a nice way of using the syntax and maintain it. You can also make function calls from here. Okay, so you can actually make a function call from here. In the static members of all classes are initialized before main function is invoked. So if you call a function from this place, it will run before your main function. That's kind of interesting thing. However, I would absolutely not recommend thinking about this technique, because if you have multiple classes and multiple places where you have static data members like this, and you're trying to initialize them like this, and in general, when you're initializing your static members, and if you're using some functions to provide initial values, the order in which these static things are initialized is unpredictable. So in other words, it completely is up to the compiler in what order these things will get their initial values. The only thing that is guaranteeing is that all static data members that exist anywhere inside or outside classes will be, if you're using function calls here or not, they all will be initialized before the main function is invoked. So just something to know about static constant data members. Okay, so what else? One more thing is that if we declare a static constant double pi inside this class, and now we have to provide initializer with double, we cannot provide direct initializer inside class body, so we have to do this in our implementation file. And notice that we have to refer to this pi variable as a member of class point. So the true name of this pi variable is pi that belongs to the scope of class point. So that's the name. Okay, but one more thing, static keyword should be dropped from this definition. Okay, so if you try to, if you decided to stick with this whole type, the static will cause an error message, and you just need to remember to remove it from the definition. Although truly inside point pi is static. So it means that it does not belong to any individual objects. It will be shared between all of the point objects created at the runtime. This is something not necessarily for outdated compilers, but it's easy to initialize integer constants using enumeration keyword. So you can research all sorts of syntax available with enumeration keyword, and enumeration could be used inside and outside of classes, and it just simply takes a name and creates an integer constant. So enum generates integer type constants, and you can provide their values. So that's just something that will become available inside class int. So this is not necessarily outdated. This is something that can be used. Constant member functions. Okay, so we've done this actually a lot. Let's take a look at, again, we'll highlight constant keyword in this file. This is the header file of Java-like string in C++. And I'll resize it to keep most of this in view. And you can see that we're using constant keyword a lot, and majority of functions, if not all of them, actually are constant. Why? Because you know that in Java, strings are immutable. Once Java Virtual Machine gives you a string, there is no way to change its content. You can forget the reference to Java string in your Java code, and your string will be garbage collected. But until then, once created, string stays the way it is. This is why, because we're trying to demonstrate a Java-like string in C++, we would like to say that whenever there is something like concatenate happens, it's not happening for the function for which concatenate was invoked. Rather, concatenate will make a copy of string which will be the result of concatenation of object for which it was invoked and some other string. So therefore, the object itself for which concatenate is invoked remains unchanged. Okay, so what it means is that if we use this concatenate example right here, and if I write code like this, I will say hello concatenate with itself, right? So now hello like is doubled. Concatenate member function invoked for hello and take some sort of argument. I think this is a little confusing. Let's just use greeting here, just other string like this, right? So we have one string and another string. And sometimes it could make an impression that concatenate modifies hello, but no, concatenate returns, right? So what it returns is that it takes greeting, which is a string of characters. It takes hello, which is another string of characters. And concatenate generates another object, which basically is the result of concatenation of these two things. And it returns back an object to the caller. But here we don't even accept this return value. So basically, the way it's written right now has no effect. So this hello is not changed. We generate concatenated string and we throw it away because we're just not accepting the result. If you want to double this hello, we need to reset it like this. Then everything will be happening because we will be dynamically updating this object by our copy constructor, which was discussed in previous series of videos. And now concatenation is used properly. And notice, this is not my choice. This is not the way I designed it. This is because we're trying to simulate a Java-like string. This is how Java-like strings behave. And we're trying to do exactly the same thing so that supposedly we can just copy and paste Java code into a C++ file and be able to compile it and be confident about all of the functionality. So there, if you want to change hello string, you have to reset it like this. Okay, and but the bottom line is that we can still write this code, but even whatever we do with this, concatenate is a constant read-only function with respect to an object for which it was invoked. And whenever is the case, and by the way, the simplest thing is a function like length. Right, so this is an example of a length function of string object. It just simply says string view, what is your length, and returns size type integer, which is just a positive integer or 0. And here there's absolutely no way to expect that the string is modified. We just return some kind of value, some sort of information about this object. So notice everywhere we use const. And this is sort of like, in my example, it's a bit of an extreme version of const, because even concatenate, which sounds like changing something, remains to be constant because it still doesn't modify this object. It needs to be reset explicitly to be modified, because this concatenate returns temporary string, which is then assigned to this object over here. So anyway, this is just something that we need to highlight over here. And the bottom line is that we use these constant qualifiers right here on every function. So character at position, return substring copy of a bunch of characters, another version of substring with the range, concatenate that generates copy of the string. All of these functions are constant, and the constant qualifier at the end of the function signature tells the compiler that this function is safe to invoke for an object which is marked constant. Okay, and therefore when we, for instance, look at the implementation of concatenation function, it takes another string, right? So when we call concatenation, it takes another string by reference. So basically, this another string becomes a reference to this original string, which was provided as a parameter. And we also say that concatenate making a promise not to change this greeting. This would be pretty ugly idea to like, you know, under some circumstances to change this object inside concatenate. To prevent that and guarantee that this is not happening, we're saying that we're promising to use it in a read-only way. But then look what we do with this another string. We start using it in this code basically, and then each function that we call, data, length, and everything, also must be declared const. So this way compiler knows that in this context where another is constant, it's okay to invoke any of its functions which are also declared constant. So this just becomes like you know, a requirement that constant function typically requires constant references if you want to call only constant functions, and vice versa. If this object provides an interface of all sorts of public functions, you would expect it to consistently mark its member functions to be constant, like we do over here, so that we can use this object in a constant context, like this example, which is very you know, straightforward type of function argument. When you have objects, you don't want to copy them, and most of the time you actually using, so therefore we're using reference, and those references are constant. So the bottom line is that you need to be careful about not neglecting you know, to specify which of the functions are constant. Like this length is a classic example. It has nothing to do with object change. It just returns information about the object. So it's a must to not to forget to add this. And if you do this and your function has the signature, just remember that we copy and paste every declaration into implementation file to write the actual code. And notice that this constant keyword continues to exist in the implementation file. So it's like this and like this. And if for some reason you want to remove this, remember that it's not going to compile properly. You will have to remove it from here as well. Okay, so this is examples of constant member functions. So constant member functions are the qualifier for them appears to be at the end of the function signature after the list of function parameters. So that's the syntax place of a constant member function. And so the next slide basically provides an example where, for example, once again, so we have some kind of function which gets string by constant reference. So string becomes a constant reference. And we are attempting to call length, and the length is declared constant. But if we attempt to use string and use append, I think it's a typo here. This should say str over here, right? So if we use this object reference and call append, this will be compiler error because append does not have constant qualifier, but we're trying to call this function in constant context. So this string deliberately was declared constant, so it's a violation of compiler rules to attempt to call any function, any member function from constant context like this, which is not constant. And this is okay, but so calling this is okay and calling this is not okay. It will be a compiler error.